So hi, my name is Olivier Boulle from SPINTEC in Grenoble, France. And in this talk, I would like to present our last results on skyrmion racetracks defined by light ion irradiation and antiferromagnetic skyrmions for logic and memory application. So first, I would like to thank the organizer for giving me the opportunity to present this work. And I will be there in Cefalù in September, so I will be happy to meet you and talk about our results. So first, I would like to introduce magnetic skyrmions and explain why these spin textures are so interesting. So in magnetic material, the ferromagnetic or antiferromagnetic order arises from the exchange interaction, which tends to align neighboring spins parallel to each other. But in some materials, which are characterized by the absence of symmetry inversion, as well as spin-orbit coupling, a chiral exchange interaction can arise, which favors a 90-degree orientation alignment between neighboring spins and tends to make them rotate with a given sense of rotation. And the competition between these two terms can destabilize the ferromagnetic state and stabilize novel spin texture, such as this continuously rotating spin spiral, as well as magnetic skyrmions. So magnetic skyrmions are bidimensional chiral whirling of the magnetization. So you can see here a schematic picture of magnetic skyrmions, where the spin at the outer edge are oriented upward, the spin in the center are oriented downward, and as you move along the skyrmion diameter, the spins are continuously rotating, describing this spin spiral with a given sense of rotation. So it's a chiral object, and this chirality being driven by the Jalowski-Moria interaction. So magnetic skyrmions have also some topological properties, so they cannot be continuously transformed toward the ferromagnetic state without causing a singularity, and this provides stability to the magnetic skyrmions, since you need to overcome an additional finite energy barrier due to this topology to annihilate the skyrmions. And this topological property is quantified by the topological charge, which counts the number of times the skyrmion's spin texture is wrapping the unit sphere in the spin space. So a skyrmion is mapping the unit sphere once, so that this charge is 1, while it is 0 for a ferromagnetic state. And finally, magnetic skyrmions can be very small, down to the nanometer scale, as you can see here on this picture of skyrmions in a palladium iron ultra-thin films, which was obtained by the group of Professor Wiesendanger. So an additional important feature is that skyrmions can be manipulated by in-plane currents, which has led to novel concept of non-volatile magnetic memories and logic devices where skyrmions in nanotracks are the information carriers. So the nanometer size of the skyrmions, combined with their fast manipulation with current, could lead to devices with a unique combination of high storage data density, large data throughput, and low power consumption. However, several key challenges still need to be tackled to realize such devices. First, one needs to be able to stabilize very small skyrmions, typically down to 10 nanometers at room temperature and zero field, in industry-compatible materials. Second, you need to be able to manipulate these skyrmions fast, with low power and with reliable motion. Finally, to write and read the information, you need to be able to write to achieve controlled nucleation and annihilation with fast and low power excitation. So recently, the demonstration of room temperature skyrmions in ferromagnetic heavy metal ultra-thin films, as well as their current-induced manipulation, have lifted an important bottleneck towards the realization of such devices. This class of material combines several advantages for devices based on magnetic skyrmions. Firstly, the breaking of symmetry inversion at the ferromagnetic heavy metal interface, combined with the large spin-orbit coupling in the heavy metal, leads to a large Jalowski-Moria interaction combined with large spin-orbit torque, meaning efficient current-induced motion. In addition, these materials can be deposited by sputtering deposition, and they are also CMOS compatible and are commonly used in the MRAM industry. So magnetic skyrmions have been observed at room temperature in various declinations of this material system, such as single or multiple repetition of platinum cobalt multi-layers with different capping layers to break the inversion symmetry. So in this system, the skyrmions are stabilized by stray field energy, and this favors larger skyrmions with size ranging between 15 nanometers and a few microns. And actually, this is quite large for application. In addition, an external magnetic field is needed to stabilize them, which cannot be easily implemented in a device. Current-induced motion have also been demonstrated in this class of materials with velocity over 100 of meters per second. And the force that drives the skyrmion dynamics here is due to the spin-Hall effect, where the charge current which is flowing in the heavy metal is converted into a spin current due to the large spin-orbit coupling, which is then absorbed by the ferromagnetic layer. And this leads to a force along the current direction. In addition, the topology of the skyrmion leads to an additional geotropic force here, which is perpendicular to the skyrmion velocity. And it results in a motion transverse to the current direction. And this transverse motion is also known as the skyrmion Hall effect. So you can see on the movie here that the skyrmion move in the current direction, but they have also a motion which is along the right side of the track. And actually, so this is an important issue to manipulate skyrmions in track, since they can be annihilated on the edge of the track, so that you would lose your information. In addition, although skyrmion velocity around 100 meters per second have been demonstrated, this is still too slow for device application where velocity larger than 1000 meters per second would be needed. So in this talk, I would like to address different approaches in order to lift these limitations, and in particular, this skyrmion Hall effect. Firstly, I will show that skyrmions can be nucleated and guided in racetracks using local helium-ion irradiation, which allows to get rid of the skyrmion Hall effect. Another promising approach lies in the stabilization of antiferromagnetic skyrmions in synthetic antiferromagnet with vanishing zero vector. And I will show that skyrmions can be stabilized at room temperature and zero field in this material, and can be nucleated locally using current injection or ultra-fast laser excitation. And finally, I will show that magnetic skyrmions can be imprinted directly within an antiferromagnet using exchange bias, which opens a new way to manipulate skyrmions in antiferromagnet. Okay, so first part, nucleation and guiding of skyrmions using local helium-ion irradiation. So the material system we have considered for this study is a platinum cobalt MgO tri-layer ultra-thin film. And we have shown in a previous study that this material is characterized by a large Jablonski-Morier interaction, which is around 2 millijoules per square meter, which allows us to stabilize magnetic skyrmions with a Néel chirality at room temperature. And the large spin-orbit torque in this material also leads to fast motion up to 100 meters per second. And we were able to observe the skyrmion Hall effect in this material. So this can be seen on this image, for instance, where the successive injection of short current pulse in a track leads to the motion of the skyrmion. So here you can see the yellow guy. Okay, it's moving down, but also toward the left of the track, okay, due to the skyrmion Hall effect. So we observe that the skyrmion Hall effect is drive dependent. At low velocity, it is reduced due to pinning on defects in the material, while at larger current in the flow regime, a deviation of about 50 degrees is observed with respect to the current direction. So a way to get rid of the skyrmion Hall effect is to guide the skyrmion in potential well defined in the material. And this can be achieved by changing locally the magnetic properties of the material using light ion irradiation. So in these ultra-thin films, the magnetic properties, such as the magnetic anisotropy and the DMI, arise from the interface. And light ion irradiation allows a gentle modification of the interface by atomic intermixing, thereby changing locally the magnetic properties. And we observe that in our ultra-thin film, so in our platinum cobalt MgO film, the helium irradiation leads to a decrease of the perpendicular magnetic anisotropy. And the larger the dose, the larger the decrease. So you can see here on the right side that increasing the dose leads to a progressive bending of the hysteresis loop, illustrating the decrease of the perpendicular magnetic anisotropy. And for larger dose, the magnetization goes in the thin plane. So we have also characterized the impact of the ion irradiation on the DMI using systematic Brillouin-like scattering measurements. And we observe that the ion irradiation leads to a slight decrease of the DMI. And this is in line with a recent ab initio calculation from the group of Stefan Blugel, where a similar drop of the DMI is observed after intermixing the interface. So this combined decrease of the DMI and magnetic anisotropy induced by helium ion irradiation can be used to pattern local potential well for the skyrmion. So to this end, we have a pattern 150 nanometer wide track using helium ion focus ion beam with a sputtered platinum cobalt MgO film. So atomic force microscopy experiments show that this FIB only leads to locally to a small increase of the roughness. So we don't etch the material. And we then characterize the domain structure for different perpendicular magnetic fields using magnetic force microscopy. At remanence, striped domains are observed, but when applying small perpendicular magnetic field, the non-irradiated part saturates due to the larger perpendicular anisotropy, while striped domains align along the irradiated tracks. So increasing further the field leads to separation of this warm domain into a single array of isolated skyrmions in the track. And actually, they can be compressed towards smaller sizes down to 35 nanometer by applying a larger magnetic field. So to get more insight into this experimental result, we performed micromagnetic simulation with MUMAX code using experimental parameters. Yes. So we simulated ion irradiated track, the ion irradiated track by a 150 nanometer wide region with lower PMA and DMI. And the simulation well reproduced the initial state at remanence where Worm's domain are observed in both irradiated and non-irradiated region. Then, as the external out-of-plane field is increased, the Worm's domain shrink along the irradiated region with reduced PMA and DMI, acquiring an elongated shape along the track, while the non-irradiated region is saturated, as is observed experimentally. And as you further increase the magnetic field, the skyrmions acquire a circular shape, which is explained by the reduced influence of the confinement potential when the skyrmion becomes smaller than the track width. So as is observed experimentally, of course, the larger the field, the smaller the skyrmions. And we have also studied the influence of the fluence, irradiation fluence on the skyrmion diameter. So the larger the fluence, the larger the skyrmions, which can be explained by the reduced dominal energy at larger fluence due to the reduction of the perpendicular magnetic anisotropy and the DMI in the irradiated part. So we have also studied the current-induced dynamics of these skyrmions. So the images show the current-driven motion of a few skyrmions in irradiated tracks, so in red here, at two different angles with respect to the current direction, 0 degree and 22.5 degree. For each sequence of image, 11 nanosecond current pulse is injected in the direction indicated by the arrow. And remarkably, upon changing the current direction, the skyrmions move back and forth within the irradiated track. And the skyrmion velocity is around 35 meters per second. And for this velocity, one expects a skyrmion Hall angle of around 30 degrees. However, you can see now that the skyrmion angle here is 0. Thus, the track acts as a local potential well that guides the skyrmion trajectory, which allows us to suppress the skyrmion Hall effect. So to better understand these results, we carried out micromagnetic simulation using experimental parameters, and the simulation will reproduce the observed guiding of the skyrmion dynamics in the track. In the first few nanoseconds, the skyrmion injection, the injected current leads to a skyrmion motion along the track direction, as well as a transverse motion towards the edge induced by the gyrotropic force. After a few nanoseconds, the skyrmion encounters the track edge, and the energy barrier at the edge generates a force opposite to the gyrotropic force, suppressing the transverse motion, such that the skyrmion starts to slide along the edge without skyrmion Hall effect. So as you can see here also. So I compare here the skyrmion velocity with and without tracks. And interestingly, the skyrmion move around twice faster in tracks compared as without track. So the cancellation of the gyrotropic force boosts the longitudinal skyrmion velocity. However, what we observe also is that above some threshold current density, the energy barrier is not large enough to compete with the gyrotropic force, and the skyrmions are expelled out of the racetrack. This is what happens here. Nevertheless, these simulations show that this threshold can be easily tuned by varying the barrier height, for instance, by increasing the anisotropy of the pristine film. So we can see here that increasing the anisotropy field in the non-irradiated area brings the maximum velocity from 25 to 65 meters per second, without affecting much the dependence of the velocity on the current density. So the maximum velocity for skyrmion motion in the irradiated track increasing monotonously with the anisotropy field, and the simulations also show that the magnetic damping has a large impact on the skyrmion dynamics. So lowering the damping from 0.3 to 0.01 leads to a large enhancement of the skyrmion velocity by a factor of about 20. So however, the maximum velocity which is attainable before the ejection of the skyrmions is not significantly affected by this damping. So to explain this result, we have considered a simple analytical model based on Thiele equation. And assuming that the skyrmion radius is large compared to the domain wall width, this leads to this simple expression of the skyrmion velocity in the track. So you can see that the velocity scales as 1 over the magnetic damping, which explains the large increase of the velocity when decreasing the damping. So the gain in velocity in an ion defined racetrack compared to a confinement-free motion also scale as 1 over the damping. So assuming a damping of 0.01, a gain of about 40 can be expected for typical skyrmions. Okay, so note here that in our experiment we expect a much larger damping, about 0.3. Okay, so that which explains that a much lower gain is obtained in our for our experiment. So to conclude this part, light ion irradiation offers a new method to stabilize skyrmions in track and guide their motion with no skyrmion Hall effect. Now I would like to address a second promising approach based on antiferromagnetic skyrmions in synthetic antiferromagnets. So what are synthetic antiferromagnetic skyrmions and why are they interesting for skyrmions? So a synthetic antiferromagnet consists of two ferromatic layers antiferromatically coupled through a thin non-magnetic spacer. Now, a skyrmion in a SAF is actually a bilayer skyrmion where the two skyrmions share the same chirality, but with opposite topological charge. So opposite polarity. As a result, they are expected to be driven along the current direction without skyrmion Hall effect because the gyrotropic term cancels out if the SAF is compensated. So this cancellation allows to speed up the skyrmion velocity and faster motion of skyrmion is predicted in this stack. And finally, the vanishing magnetic moment of the skyrmions leads to small stray field. And since the stray field energy tends to make skyrmion larger, smaller skyrmions are expected in SAF. So to observe skyrmions in SAF, the first step was to optimize the magnetic stack. So the stack we have considered was composed of a sputtered platinum, cobalt, nickel, iron, cobalt layer, which was antiferromatically coupled to a platinum cobalt layer through a thin ruthenium layer to achieve RKKY antiferromatic coupling. So as you can see, we use here different materials for the ferromatic layer, which allows the direct observation of the skyrmions in the different antiferromatic coupled layers using scanning transmission X-ray microscopy by tuning the energy of the X-ray beam. So a platinum cobalt interface was chosen in order to get a large perpendicular anisotropy and Jansky-Morian interaction. And the thickness of the layer was adjusted so that it is fully compensated. And both layers are close to the out of plane and to in-plane transition, which allows us to reduce the domainal energy and to facilitate the nucleation. So this small anisotropy leads to stripe domain at remanence, as you can see on this STXM image. So one can see opposite decoy contrast at the cobalt and the iron edge, which demonstrates the antiferromatic coupling of both layers. In addition, you can see that skyrmions spontaneously nucleate in this stripe domain texture, as shown here in the upper part of the image. Isolated skyrmions can also be nucleated by injecting current pulses or after saturation using a large magnetic field. So for instance, an isolated skyrmions can be seen on this STXM image measured after saturation by a large magnetic field. So you can see here a zoom image on these skyrmions, one taken at the iron and one at the cobalt absorption edge, measured by ptychography reconstruction. So the opposite magnetic contrast demonstrates the antiferromatic alignment of the skyrmion magnetization in the two layers. So I show you here a line scan along the skyrmion diameter at both the iron and cobalt edge, which superimpose accurately. So this demonstrates that this is an antiferromagnetic skyrmions in a SAF, stable here at zero field and room temperature. So we repeated this experiment several times, and it allowed us to obtain the distribution of the skyrmion sizes with an average diameter of around 205 nanometers. But actually, these experiments raise several questions. First, the skyrmions are not so small, with an average size of around 200 nanometers, while, as I told you, small skyrmions are expected in SAF. Second, the STXM does not allow us to determine the chirality of the skyrmions. We are only sensitive to the perpendicular component of the magnetization. So the questions are why the skyrmions are larger and are there real chiral skyrmions? And to answer these questions, we carried out a micromagnetic simulation using parameters that were measured experimentally so that we can mimic the experiments. An important result is that the simulation predicts that skyrmions are stable in our system and there are homochiral Néel skyrmions in all the layers. And the simulation also reproduces the tri-domain structure and the average skyrmion diameter of around 200 nanometers, so it is close to the experimental ones. So now, why are they large and how to make them smaller? So in these ultra-thin films, it is well known that the different magnetic energy that control the skyrmion size and energy depend strongly on the film thickness, in particular the DMI and the magnetic anisotropy, which are of interfacial origin. So we did some micromagnetic simulation of the skyrmion size and energy as a function of the film thickness, so which corresponds to this red dot here. And you can see that there is a large variation between 10 nanometer and 200 nanometer over a narrow range of thickness. And the stability energy follow also the same trend. And to better understand these results, we have built a model which provides an analytical expression of the skyrmion size and the stability energy, which actually is in nice agreement with the simulation. So this is the black line here on the figure. So this model shows that there are two important quantities which control the skyrmion size and energy. First, the domain width, and second, the ratio of the GMI over the critical D, so DC, where DC is a critical GMI for the appearance of spin spiral. So we have plotted these two quantities here on this figure, and the divergence of the skyrmion radius and energy can be explained by the fast increase of these two quantities, so in particular D over DC, with the film thickness, as we are approaching the in-plane to out-of-plane reorientation transition, so when the anisotropy is vanishing. So in our thin film, we are a bit too thick, so close to this transition here, and so a way to decrease the size of the skyrmions is to decrease the film thickness such that a typical size around 10 nanometer could be achieved with a relatively high thermal stability. So in previous experiments, the ground state was a striped domain state, and the skyrmion nucleation by current occurred randomly in the track. However, for a device, the ground state should be uniform state, where isolated skyrmions can be nucleated and annihilated in a controllable way. And to achieve this, we optimize sample with a large perpendicular magnetic anisotropy, such that a monodomain state is stabilized at remanence. And to nucleate the skyrmions, we pattern a thick gold electrode on top of the magnetic stripe with a triangular shape. And when injecting current pulses, the large current density at the apex of the tip leads to the local nucleation of the skyrmion under the tip. And when injecting a second pulse, the opposite polarity, with the opposite polarity, the skyrmion can be nucleated, can be annihilated, sorry. So this process is very reproducible. So this experiment demonstrates the reproducible antiferromagnetic skyrmion nucleation and annihilation induced by current pulses in fully compensated SAF at room temperature and zero field. So to better understand the dynamics of the nucleation, we carried out pump probe STXM experiment at the Maximus beamline in Bessie synchrotron, which allows the time resolved imaging with very high time resolution, down to 125 picoseconds. So you can see on the animation the time resolved nucleation of the skyrmion induced by the injection of a 3 nanosecond current pulse. And this process is highly reproducible and is observed over 10 billion cycles. And the current injection leads to the nucleation and a fast increase of the skyrmion size, followed by a slow relaxation when the pulse is turned off due to the domain surface tension. And we did some systematic measurement of the dynamics as a function of the current amplitude, which allows us to extract the time dependence of the skyrmion dimension and area for different current densities. So another way to nucleate magnetic skyrmions is through ultra-fast laser pulse illumination. So we have already shown the local nucleation of skyrmion bubble lattices in ultra-thin tantalum iron covalent boron tantalum oxide film by ultra-fast laser pulses. And the laser pulse leads to ultra-fast demagnetization, which relaxes into skyrmion lattices in this multilayer. So importantly in this experiment, the skyrmion bubble state were metastable state, and it was not reachable using a magnetic field, so only by ultra-fast laser pulses. So ultra-fast laser pulses provide a tool to nucleate magnetic skyrmions from the uniform state, which is what you want for a device. And we have shown that this can be also used to nucleate SAF skyrmions in compensated platinum cobalt ruthenium SAF multilayer. So given the SAF skyrmions are much smaller and difficult to observe, we use X-beam microscopy with in situ laser excitation. And starting from a monodomain state, we are able to nucleate locally isolated SAF skyrmions, as well as skyrmion lattice by illuminating by 100 femtosecond laser pulses. So diameter are typically here 150 nanometer. Yeah. Okay, so this concludes my part on antiferromagnetic skyrmions in SAF. And finally, I would like to show that antiferromagnetic skyrmions can also be stabilized directly in an antiferromagnet with exchange bias system. So another way to stabilize antiferromagnetic skyrmions is to consider antiferromagnet where a larger stability is expected due to the larger exchange field. However, the skyrmions are very difficult to nucleate, and their observation in antiferromagnet is very challenging due to their vanishing magnetic moment. And to nucleate this spin texture in the antiferromagnet, we have used exchange bias structure composed of a platinum cobalt nickel iron layer, which is hosting skyrmions in contact with an iridium manganese antiferromagnetic layer. So the skyrmions are imprinted from the ferromagnetic layer into the antiferromagnet by annealing above the blocking temperature and then by cooling it down. So after annealing, we have exchange bias field, so here of around 50 millitesla. And using a BLS experiment, we measure a DMI of around 0.3 millijoule per meter square that can stabilize NEL left-handed domain walls and skyrmions. And to observe the skyrmions, we have used the X-ray magnetic microscopy technique, XMCD PIM. And by tuning the X-ray energy at the iron edge, we are able to observe the magnetic skyrmions in the ferromagnetic layer. And when looking at the manganese edge, corresponding skyrmionic texture are observed also, which corresponds to the XMCD signal of the interfacial non-compensated spins in the iridium manganese antiferromagnet. So this result demonstrates the replication of the magnetic skyrmions into an iridium manganese antiferromagnet using exchange bias. And so this concludes my talk. So in this talk, I have shown different approaches to manipulate magnetic skyrmions in racetrack. Firstly, I have shown that skyrmions can be nucleated and guided in racetracks using local helium-ion irradiation, which allows us to get rid of the skyrmion Hall effect. Another promising approach lies in antiferromagnetic skyrmions in synthetic antiferromagnet with vanishing zero vector, and I have shown that SAF skyrmions can be stabilized at room temperature and zero field in this material and can be nucleated locally using current injection or ultrafast laser excitation. And finally, I have shown that magnetic skyrmions can be imprinted directly within an antiferromagnet using exchange bias, which opens a new way to manipulate skyrmions in antiferromagnets. And finally, I would like to conclude with and acknowledge all the people who have been working on this topic and with allows to get these nice results. In particular, Romeo Juge. So most of the results obtained here were obtained during the PhD phases of Romeo Juge. And I also would like to acknowledge Liana Prejbanu and Navin Sisodia for the micromagnetic simulation, as well as Kaushik Beragi. So this work was done with a lot of collaborators and lots of collaboration, in particular with NEL Institute, the University Paris 13 Mohamed Megenai for the BLS experiment. The helium irradiation were done at spin ion technology. All the X-ray magnetic microscopy were done in several beamlines in Europe, which are listed here. And with this, I thank you for your attention, and I'm looking forward to meeting you in Cefalù or on Zoom in September. And thank you very much.